My name is Emma Mirizio. I'm a PhD candidate at the University of Maryland, and I work at NASA Goddard Space Flight Center studying the Aurora with sounding rockets. So today I'm going to introduce you to the Aurora a little bit, and then I'll talk to you about the GIRAFF sounding rocket mission, which we launched earlier this year. Then I'll talk about a specific instrument on the GIRAFF sounding rocket mission and how we answer our big questions, our big science questions with that instrument. And then I'll leave you with our future work and what's next for our group. First, I wanted to talk about the auroral origins, where the aurora comes from. And down here in the bottom right is a video I took in 2023 during a different sounding rocket campaign of the aurora, so you can see how fast it moves, how dynamic it can be, and all of the different colors that we can see in the aurora. So we start at the sun. This is where the aurora comes from. And as we zoom out, we can talk about the solar energetic particles, the electrons and ions that are streaming from the sun at all times that eventually reach Earth and give us the aurora. So as we zoom out, we're imagining all of these solar particles streaming out from the sun, zooming in towards the Earth. And Earth has this awesome thing called a magnetic field. And this magnetic field, which is represented by these lines coming from both of the poles of the Earth, protects us from radiation, protects us from these energetic ionizing particles, this energetic radiation. And in doing that, it can stream these particles, we'll talk about electrons in specific, towards the poles. So if we zoom in, we can look at the electrons streaming in towards the poles of Earth. And it's because of this that we see the northern lights and the southern lights, so the Aurora Borealis and the Aurora Australis at the northern and southern poles of the Earth. If we zoom in even farther, we can talk a little bit about the atmosphere, the ionosphere of Earth, which is a little bit above the weather layers of the atmosphere, a couple hundred kilometers above the Earth. And I'm going to talk specifically about the most abundant particles in our atmosphere, so nitrogen and oxygen. And in this layer of the atmosphere, we have these particles at a ground state. They're not ionized right now, but this constant stream of particles coming from the sun energizes these. So we have these electrons streaming in from the poles, hitting these particles and energizing them out of their ground state energy levels. So when they reach higher energy levels, they don't really want to be in those higher energy states, and they would do anything to get back down to their ground state. And how they do that is by releasing energy in the form of photons. So the reason I chose these particles in particular is because they emit photons in different colors of light that we would tend to see in the aurora. So atomic oxygen, the O represented here, releases the most common color that you might see in the aurora, bright green. And so that's the wavelength of light that it emits when it gets energized and then goes back to its ground state. And then also molecular nitrogen, which is the most abundant molecule in the atmosphere. And when it gets energized and releases back to its ground state, it emits red and blue photons. And when we combine red and blue, we see a purplish or a pinkish magenta aurora. So now if we zoom back out, back to the atmosphere, there we go, we get the aurora. So this is a video from, again, that 2023 launch of the rockets. So this was a rocket called Dissipation, and you'll see a flash in a second in the center of this field of view of that rocket launching and going through the camera. There it is. And this is an auroral substorm, so a really bright happenstance of aurora that creates all of these interesting and dynamic auroral lines. Now that we understand what the aurora is, I want to talk specifically about the GIRAFF mission. So this is a mission that we launched in January or early February of 2025. It's 2 sounding rockets that flew through space over Alaska through the aurora and measured the electrons and ions that create the aurora. So if we look at these images, we see the rocket flies above in space above Alaska. We launched from about an hour outside of Fairbanks, north. That star is where Poker Flat is. That's our research range. This was a video of the launch of the rocket. So we launched into clouds, but it was thankfully clear where our ground stations were. So we got some great videos of the aurora. This is explaining a past mission, actually. So the videos in the top right explain the types of aurora that we are trying to detect with the GIRAFF mission. So GIRAFF I should explain what it stands for. It's the Ground Imaging to Rocket Investigation of Auroral Fast Features. And those fast features that we're trying to investigate are the flickering and the pulsating aurora. So on the top left here, in this top right corner, we see flickering aurora. It kind of looks like TV static, and it can be up to 15 hertz, so flickering on and off at 15 times per second. And then on the very top right over here, we have the pulsating aurora. The fast pulsating aurora can pulse in and out over a couple of seconds or even slightly less than a second. And these are two different phenomena that we don't really understand very well why they happen. And so these are what these two rockets were aiming to investigate by looking at the particles that create the aurora. So in the bottom right here, we just have the two payloads of the rockets. And in a second, we'll zoom in on those two payloads and see what's inside of them. So that brings us to APES. APES stands for the Acute Precipitating Electron Spectrometer. And that's a fancy word for it takes in electrons and tells you what energy and how many of them there are. So this is an image of the instrument before we put all the panels on, so you can see some of the electronics inside of it. And now let's look at how it works. So here we have the rocket on the launch pad, and APES sits at the very top of the rocket. So underneath the nose cone, we have this pointing directly outward from where the rocket is launching. And then if we zoom in, we can see what's inside of it. So at the bottom, we have a magnet in the bottom section of the APES housing, and the electrons stream in through the aperture. And as the electrons go in, they hit a detector plate. And because we know that magnetic fields alter electric fields, and we can bend the flow of the electrons as they're entering the APES instrument, and depending on how energetic the electrons that are coming in are, they get bent by different amounts. So that's how we determine the different energies of the electrons in the instrument, is they land on different parts of the detector depending on how energetic they are. And that's how we can see how many electrons and how much energy they have. So now we come to the results. So this is the first images of the electrons that are streaming in from this instrument. So here we have, as the rocket is flying through space, the APES instrument is collecting all of this data. And we have the really low energy electrons at the bottom here and the really high energy electrons at the top. And the color of them, if it's a brighter color, that's how energetic they are. So we can watch that video one more time. These are the electrons streaming in. We see different auroral features as we go through this video, and I'll explain them more in a second. So then this is everything all together. So as this little animation of a rocket is flying through the sky, the rocket is going through the field of view of this optical camera, and APES is collecting all of this data as it flies through here. So we can see some different interesting auroral features in the optical camera. So this is the first rocket that we launched. And we can see some flickering and pulsating events in the optical, as well as these interesting features that must correlate to what we're seeing with the scientific instruments on board. And now just zooming in on the entire rocket flight of what APES collected for this first launch. We have energy levels from a few hundred electron volts all the way up to 30 keV. And we have all of these interesting features. So in the future, when we put all of this together, we'll be able to see what each of these tiny little features correlates to from the optical data, what we actually see that the rocket flew through in the imaging. So we have some different auroral features, as well as some maybe pulsating aurora up here where it comes in and out and in and out. And that'll be exciting to dig through in the future. So now I just wanted to say one thing about what we're planning for next year. So in February, in about 2 months, we're launching a rocket, and it is the Black and Diffuse Auroral Science Surveyor. And I'll let you figure out that acronym for yourselves. And this is targeting black aurora, which is these sort of upgoing electrons, so these negative features where there's a little bit of an absence of aurora within the aurora. And finally, I just wanted to say thank you to our entire team, because I can't do this by myself. And here's a bunch of pictures of us building the rocket and flying it. So thank you.
All right, that was awesome. Congrats again to our 4 presenters this afternoon. That concludes our student visualization program competition for today. And we will start back with our science presentation.